Greetings, science enthusiasts. This video, created by artificial intelligence, explores the fascinating world of helium atoms. Please excuse any script errors or irrelevant media. To kick things off, let's start with the basics. A helium atom is composed of 2 electrons, 2 protons, and 2 neutrons. Quite simple, right? But as with most things in science, there's more to it than meets the eye. The protons and neutrons make up the nucleus of the helium atom. These are held together by a fundamental force in nature known as the strong force. It's an apt name, as this force is indeed the strongest force in the universe, even more powerful than gravity. It's the glue that holds the nucleus together, and by extension, the entire atom. Swirling around this nucleus are the 2 electrons. They're bound to the nucleus by the electromagnetic force, a different fundamental force. These electrons exist in a cloud-like region of space around the nucleus, moving at incredible speeds. It's this rapid movement and the uncertainty of their exact location that brings the strange world of quantum mechanics into play. The strong force, the electromagnetic force, the protons, neutrons, and electrons all come together to form the helium atom, an essential component of our universe. This, in essence, is the basic structure of a helium atom. But, as we'll see in the upcoming sections, the complexity of helium atoms extends beyond their basic structure, delving into the realm of quantum mechanics. So stay tuned for more fascinating insights into the world of helium atoms. Quantum mechanics plays a crucial role in understanding helium atoms. To unravel the mysteries of this multi-electron system, we dive into a world of complex calculations and intricate equations. The quantum mechanical description of helium is like a challenging yet fascinating puzzle waiting to be solved. Consider the Hartree-Fock method, one of the mathematical techniques used to estimate the properties of helium. Named after the brilliant minds of Douglas Hartree and Vladimir Fock, this method uses wave functions to approximate the behavior of electrons in multi-electron atoms like helium. It's a bit like trying to predict the movements of dancers in a ballet, where every performer influences all the others. But the Hartree-Fock method isn't the only tool in our quantum toolbox. There are other methods, each with its own strengths and weaknesses, offering different perspectives on the same problem. The choice of method often depends on the specifics of the problem at hand. For example, in the case of helium, the Hamiltonian, or total energy operator, involves a 3-body system, 2 electrons and a nucleus. This makes the problem exponentially more complex, as it requires accounting for the interactions between all 3 particles. And then there's the matter of symmetrization postulates and spin states. These influence the solutions for the helium atom and add another layer of complexity. The energy levels of helium are influenced by the total spin values, resulting in different states. Some of these states are degenerate, meaning they have the same energy level, but different spatial configurations. This quantum mechanical description of helium, with all its complexities and subtleties, is a testament to the beauty and intricacy of atomic structures. It's like a symphony of particles, each playing its part in the grand dance of the universe. The quantum mechanical description of helium is a testament to the complexity and beauty of atomic structures. The Hamiltonian of helium is a 3-body system involving 2 electrons and a nucleus. Now, if you're scratching your head wondering what a Hamiltonian is, don't fret. It's a concept in quantum mechanics that essentially represents the total energy of a system. For helium, the Hamiltonian takes into account the kinetic energy of the 2 electrons and the nucleus, as well as the potential energy between them. Now, the Hamiltonian of helium isn't as straightforward as it sounds. It's a complex 3-body problem, and solving it involves some pretty intricate calculations. But let's not get bogged down by the math here. What's important is understanding that the solutions for helium are influenced by something known as symmetrization postulates. Symmetrization postulates are principles in quantum mechanics that dictate how particles like electrons behave. They influence the wave functions, which describe the probability of finding a particle in a particular state. This has a big impact on helium because it affects how the 2 electrons interact with each other and with the nucleus. Now, let's talk about spin states. In quantum mechanics, particles like electrons have a property called spin. This spin can influence the energy levels of the helium atom. In fact, the total spin values can lead to different states of helium, known as singlet and triplet states. These states have their own unique properties and behaviors, which are crucial in understanding the nature of helium. So you see, the Hamiltonian of helium isn't just about the total energy. It's a window into the complex world of quantum mechanics, where symmetrization postulates and spin states play a pivotal role. Understanding the Hamiltonian of helium provides a deeper insight into the behavior of this atom. The energy levels of helium atoms reveal interesting characteristics. As we dive into the quantum realm, we find that energy levels are directly influenced by an attribute known as total spin values. Now, you might be wondering, what does spin have to do with energy levels? Well, it's all about the state of the atom. In helium, the total spin dictates whether the atom is in a singlet or triplet state, which are also known as perihelium and orthohelium respectively. The singlet state, or perihelium, occurs when the spins of the two electrons are in opposite directions, canceling each other out. On the other hand, the triplet state, or orthohelium, is when the spins of the two electrons are aligned in the same direction. This difference in spins results in different energy levels for the two states. Now let's delve a bit deeper into the wave functions of these states. Wave functions can be thought of as the mathematical descriptions of the quantum state of a system. And in the case of helium, they're either symmetric or antisymmetric, depending on the total spin values. In simpler terms, symmetric wave functions mirror each other, while antisymmetric wave functions are mirror opposites. The fascinating part about these wave functions is that they determine the degeneracy of the states, which is the number of independent solutions to the Schrödinger equation that correspond to the same energy level. This essentially means that multiple states can have the same energy level, adding yet another layer to the complex quantum mechanical description of helium. So as we can see, the energy levels and states of helium are influenced by a multitude of factors, from total spin values to wave functions. These intricate details and interactions are what make the study of quantum mechanics so fascinating and important. The energy levels and states of helium add another layer to its fascinating quantum mechanical description. We've explored the basics and quantum mechanical description of helium atoms, but there's always more to learn. The world of atoms is vast and intricate, and helium, with its fascinating structure and properties, is just the start. The links provided in the description are a gateway to this atomic universe, guiding you further into the depths of helium's quantum mechanics and energy states. We're grateful to the authors and the diligent teams behind the articles from Wikipedia and Science Direct. Their enlightening content has been instrumental in our helium atom exploration. These individuals and the platforms they represent are committed to the dissemination of knowledge, a mission we share and appreciate. Our journey doesn't end here. We encourage you to delve deeper, explore further, ask questions, and let your curiosity guide you. The resources provided are just a launchpad. The universe of science is vast and holds many more secrets waiting to be unveiled. Your engagement keeps us going. Don't forget to like our videos if you find them informative and share them with fellow science enthusiasts. Subscribe to our channel and click on the notification bell to stay updated on our latest atomic adventures. Remember, to see the whole description, click on More, possibly several times if it's a long description, especially on a smartphone. If you're watching on a TV, switch to a laptop or mobile device to click the links. Thank you for joining us on this atomic adventure. Don't forget to search for American Northwest Aviation. Select the website, navigate the menu to our parent venture, American Northwest Ventures, and explore our websites. To support our channel, make your everyday purchases by accessing Amazon and our other affiliates through American Northwest Products websites, Amazon and other affiliates storefront.